When you read a research article, the results section is full of statistics, full of tables, graphs, and statistical terms. And to critically evaluate that research article, we need to have a broad understanding of what those terms mean. In this topic of your module, we're going to talk about those terms, that the common reporting of statistics that you are going to find within your research articles. So when is the last time you took a math class? Was it back in high school? Did you ever take a statistics course through college? It's okay if you haven't. That's my job, is to help you get this broad understanding of the statistics that you are going to run into in your research articles. So going back however long ago your last math class was, what's the definition of difference? What's the definition of ratio? These are two terms you're going to see a lot in your results sections. So a reminder, difference, it's just subtraction. It's 8 minus 2. That's the difference. And then a ratio is division. So in this lesson, we're going to talk about difference statistics and ratio statistics. Difference being mathematically, we got these values by subtraction. Ratio, meaning mathematically, these values were found by division. Here, these terms are the specific terms that you are going to run into, that you're going to find as you read your research article. So for difference statistics, you might see terms within your results that I've listed here: absolute risk reduction, number needed to harm, number needed to treat. For ratio statistics, relative statistics, odds ratios, hazards ratios. Keep your eye out for those. We're going to talk specifically about each of them. So today's objectives are, we're going to identify difference statistics and ratio statistics. So I want you to remember, you're not a statistician. I'm not a statistician. Researchers hire statisticians. It's its own field because it's complicated. It is a degree and field in and of itself. So you don't need to know how to do calculations. You already do know how to subtract and divide. You don't need to know how they got there, but you need to know how to interpret the results that are there. I want to give you a helicopter view, a looking down on it view of statistics, to understand that results section that you read, to understand the significance of the statistical values that are utilized, to be able to understand what is being communicated. Let's take a look, helicopter view look, at a few results sections and see what kind of statistics are being presented. So let's jump down to the results section. Here's our results. Here's the baseline characteristic table that you find in each study that we have already discussed previously. Looking at table 2, we find group difference. Also, I see hazard ratio, relative risk ratio. This figure represents our hazard ratio. Let's look at one more study and see what statistical tests were chosen for that one. Here's our results in our baseline characteristics table. Our first figure represents the relative risk. In table 3, we also see relative risk. The common term you're going to see here is the confidence interval, or the CI. We are going to get into that next week in Module 5. We're going to put it aside for now and talk in depth about it in the next module. In our helicopter view, that first article represented results in group difference. That is a difference statistic. So we're going to start in difference statistics. And difference is just subtraction mathematically. We're going to look at absolute risk reduction, number needed to treat, and number needed to harm. The key terms in this study that refer to absolute risk reduction are absolute or difference. Both of these terms mean that this result was calculated using subtraction. Sometimes you'll see an absolute difference. You'll see a risk difference. Again, there's your key term, difference. You'll see an absolute risk difference. You'll see absolute risk reduction, absolute being that key term. All of those mean the same thing, that your result was calculated via subtraction. The calculation is usually the intervention result minus the control result. So let's take a peek. We looked at this article briefly on our helicopter view, the effects of vitamin D supplementation on severe asthma exacerbations with children with asthma and low vitamin D levels. So this table has your intervention result, vitamin D, your control result, which is the placebo. And then you see, let me point it out here, our result is group difference. Key term, key word in there, difference. That means subtraction. Let's look at this first result. We get negative 13.1. Where's that come from? So here on the left, our primary outcome is days to severe exacerbation. Our intervention results, the mean is 240, the placebo 253. And that's where we get our negative 13 group difference, 240 minus 253. Obviously, these values here have been rounded in the table since we have a decimal point here. In parentheses is our confidence interval. We will discuss and go into depth on confidence intervals next module. But keep it in mind that that's what we're looking at here in parentheses. Let's do another example of absolute risk reduction. The other study that we took a helicopter look at was this ramipril study. Ramipril is an ACE inhibitor, and here in this study we're looking at the effects of ramipril on cardiovascular events. Primary outcome was stroke events in a 5-year period. Our intervention group on ramipril, 14% of patients in the ramipril group had stroke events. 18% of patients in the placebo or control group had stroke events. Represented as an absolute risk reduction, the intervention group minus the control group would be 0.14 or 14% minus 0.18, which equals negative 0.04 or a negative 4%. That's a negative 4% absolute reduction in rate of stroke attributable to ramipril. So how can we interpret the absolute rate reduction? As we do the subtraction in the absolute rate reduction of intervention group minus control group, if we get 0, then there's no difference. So taking our ramipril example, if the ramipril group and placebo group were both 14%, 14% minus 14% is 0. Or there is 0 absolute reduction in rate of stroke. Now, if the absolute reduction rate is less than 0, such as our example, 14 in the ramipril group, 18 in the placebo group, then we're seeing that there is a risk reduction with the intervention group, that those who took ramipril had a risk reduction compared to placebo. If our ARR is greater than 0, so here we have to reverse it. If the 18% of the ramipril had a stroke, where 14 of placebo had stroke, that's 18 minus 14, that's positive 4. And we're saying that there was a risk increase in the population that took ramipril. Though the negative shows a risk in reduction, the value is still presented as an absolute or a positive. So in our previous example, we would say that ramipril reduces the risk of stroke by 4% in a 5-year period compared to placebo. Our next difference statistic is called number needed to treat. Number needed to treat is the measure of how many patients need to be treated in order just to see one of them benefit. The number needed to treat is the reciprocal of the absolute risk reduction. Reciprocal is just 1 divided by that value. If the absolute risk reduction is reported as a percentage, you want to take that percentage into consideration, which is times 100. So you take 100 divided by that value. I calculated an example for you from our ramipril study. Our absolute risk reduction was 4%. So our number needed to treat is 1 divided by 0.04, or 25. Also, you can do that 100 divided by 4%, which is 25. So what's this mean? Well, this also can be stated as 1 in 25 patients saw benefit. So what's better, a higher or a lower NNT? Well, is it better that 1 in 3 patients benefit, or 1 in 25 patients, or 1 in 200 patients? Well, 1 in 3 patients benefiting is much better than 1 in 200 patients benefiting. So a lower NNT is in general better than a higher NNT. Number needed to harm is the measure of how many people need to be treated or exposed to a risk factor in order for one person to have a particular adverse effect. So instead of number needed to treat where you see the benefit, we're looking at the opposite, seeing adverse effects. In number needed to treat, a low value was good. The lower the value, the more benefit. Here, we're looking at the lower the value, the more risk, or the more harm. On a scale from 1 to infinity, 1 being low, if your number needed to harm, your NNH, is 1, that would mean that every patient exposed to that risk factor is harmed. If that number is 1,000, then 1 in 1,000 is harmed. So an example here, March et al. Showed that the antidepressant sertraline, which is Zoloft, had an NNH of 64 for suicidal thoughts when used in children and adolescents. So, said another way, 1 in 64 children and adolescents who receive sertraline will experience suicidal thoughts. So the way this is calculated is still as a reciprocal, but rather than a reciprocal of the risk reduction, it's the reciprocal of the absolute risk increase. So we have 1 over the ARI. ARI is the rate of adverse events in the intervention group minus the rate of adverse events in the control group. The number needed to harm is going to be calculated per each adverse event. So this study showed that breast cancer drug tamoxifen caused a thromboembolic event in 1 in 38 women. giving it an NNH of 138 for thromboembolic events. There were also other adverse events calculated, tamoxifan's NNH for both endometrial cancer and cardiovascular events. Now, those values were high enough that the NNH was not even reported. But as you can see, the thromboembolic event was calculated separately from endometrial cancer, separate from cardiovascular events. A quick review, NNT and NNH, number needed to treat and number needed to harm, are opposites of each other. Number needed to treat, this value we would like to be low. That means that we need to treat fewer patients before one receives the benefit. Number needed to harm, we want to be high. This means that we can treat a greater number before one of them experiences an adverse event. Moving on from difference statistics to ratio statistics, we will discuss relative risk ratio, hazard ratio, and odds ratio. Starting with relative ratio, similar to when we looked at absolute difference, our key terms here are relative and ratio. So both the terms relative and ratio indicate that the result was calculated using division. Mathematically, the relative ratio is found by dividing the intervention result divided by the control result. Relative risk ratio, RRR, is found by dividing incidence of outcome with exposure over the incidence of outcome without exposure. So essentially, it's expressing how many times more likely is an exposed person to develop an outcome relative to an unexposed person. The relative risk ratio has multiple names. It may be risk ratio, relative risk, or relative risk ratio. Key terms you're looking for again are relative and ratio. This means division. Let's look at how to interpret our relative risk ratio. When we have a relative risk ratio that is equal to 1, again, we're looking at division. So essentially 10 divided by 10 is 1. Then we're looking at 10 incidence of outcome with exposure divided by the exact same number, 10, the incidence of outcome without exposure. So that 10 divided by 10 equals 1 means there is no difference between exposed versus non-exposed. Starting at that baseline, now let's look at if it's greater than 1. Well, if it's greater than 1, that numerator, the top of the division, is greater than the denominator, the bottom. So let's call it 10 divided by 1. So here, the 10, or those in the numerator that are exposed, is higher than without exposure. That is an increased risk with exposure than without exposure. Okay, well, let's flip that. So our numerator is lower, our denominator is higher. We have 1 divided by 10 means that there's a reduced risk for those that are exposed compared to those who are not exposed. Let's just look at a couple examples with numbers and outcomes. Okay, here's an example where our relative risk ratio, the incidence of outcome with exposure, is higher or increased risk than without exposure. So here we're looking at radiation exposure, and we have 3 people diagnosed with cancer with exposure to radiation. In the denominator, 1 person diagnosed with cancer without exposure to radiation. So our 3 divided by 1 equals 3, and interpreting that, our relative risk greater than 1 means that there's a greater or an increased risk with the exposure. So with exposure of radiation, there is an increased risk of a cancer diagnosis. So here we're looking at an outcome of DVTs with an exposure of compression socks. And if we look at our relative risk, we have 5 people with a DVT who wore compression socks and 5 people with DVT who did not wear compression socks. So 5 divided by 5 is 1. Our relative risk is 1, which means there is no difference in risk between those exposed to compression socks and those not. In our last example, looking at a relative risk less than 1, we have one person with a myocardial infarction who took a statin and 4 people with an MI who did not take statin. So we have a reduced risk of our outcome, a myocardial infarction, for those who were exposed to the statin. Relative risk is called relative for a reason. It's all relative. Relative risks can be communicated poorly in a way where misinformation may spread. If we're taking a study where in that study the relative risk of 3 means something is 3 times as likely to happen if a particular intervention is applied, my general head goes, whoa, 3 times more likely, and it's pretty easy to perpetuate that into a group think fear factor. And I say here, are you impressed? Hey, if we're starting at a 30% and 3 times more likely means 90, heck yeah, I'm impressed. If we're starting at 0.1% and we move to a 0.3, are we impressed? Let's take a quick peek at a clip of this video in communicating relative versus absolute risks.
In 1995, thousands of women panicked after the UK Committee for the Safety of Medicines issued a release saying that a certain kind of contraceptive pill doubled the risk of a venous thromboembolism. That's the result of a blood clot. Thousands of women stopped taking their pill, and the result later on was a big spike in abortions in the UK. Let's look at how that risk could have been communicated better. The claim of a doubling of risk is known as a relative risk, and these are very often used by the media. But the problem is that it's impossible to interpret this doubling and know its importance without knowing what doubled what. And for that, we need to know the absolute risk of a venous thromboembolism in the group of people not taking a pill. And at the time, this was estimated to be about 1 in 7,000. So the doubling takes that up to 2 in 7,000 in the group of women who are taking that contraceptive pill. So the increase in absolute risk is 1 in 7,000. And this, to be honest, is fairly small. We think this is a much better way to communicate that risk, and perhaps if it had been done that way in 1995, there would not have been such negative consequences.
Our second ratio statistics is odds ratios. Odds ratios are used to determine whether an exposure is related to a disease. So it's used most often in case control studies to help researchers work backwards. So in other words, here's a disease, let's see what's associated with it. An example in history that you would be very familiar with is lung cancer and its association to smoking. Researchers saw the prevalence of lung cancer, used odds ratios to determine the association of smoking to lung cancer. So by formal definition, odds ratios tell us how many times more likely we are to find a particular exposure, smoking, in someone with a disease, lung cancer, compared to finding that same exposure in someone without the disease. Calculated, you should expect that it's division. Odds ratio is odds of exposure in those with the disease divided by odds exposure in those without disease. You're not going to have to know or figure out how to actually get odds of exposure, but you do need to know that this is a ratio that we are getting the final result via division of those with disease, without disease. The more important thing to know is what to do with an odds ratio. So how do we interpret? With an odds ratio of greater than 1, this means that the exposure is associated with higher odds of the disease. So looking back at smoking and lung cancer, there the odds ratio would be greater than 1. If the odds ratio is 1, then the interpretation is there's no difference in odds of disease occurring, whether exposed or not exposed. Finally, if our odds ratio is under 1, we are now saying that exposure associated with lower odds of the disease. And therefore, it would be more of a protective factor against the disease. So let's practice. You're reading a research article and you find an odds ratio of 1.98. How do you interpret this finding? A, the exposure increased the odds of the disease occurring. B, the exposure decreased the odds of the disease occurring, where it was protective. Or C, the exposure did not appear to have any effect on the odds of the disease occurring. A is correct, that this exposure is a risk and increases the odds of the disease occurring. All right, again, you run into an odds ratio as you're reading your research article. It is a 0.75. The exposure increase the odds of disease? Does the exposure decrease the odds of the disease? Or is there no effect? We are below 1, so this exposure decreased the odds. It was protective.
One of those confusing terms that you find in medical papers is the hazard ratio. And I'm going to take you through the hazards of the hazard ratio with the help of these. In 2019, chili peppers made the headlines, and all because of a hazard ratio. CNN said eating chilies cuts risk of death from heart attack and stroke. The Mirror, eating spicy food cuts your risk of early death by a quarter. While The Independent said that chili eaters have fewer deadly heart attacks, say scientists. These headlines all came from research published in the Journal of the American College of Cardiology, who quoted a hazard ratio of 0.66. But what does this mean? A hazard ratio is a number that compares the rate at which an event happens in two different groups. In this study, the two groups were people who hardly ever ate chilies and those that were eating chilies more than 4 times a week. That's a lot of chili sauce. And they looked at 23,000 people over 10 years and compared the rate at which they had a heart attack or stroke and then died in those two different groups. So let's look at a plot. Here's a graph which along this axis shows the years for which the people have been followed up to 10 years. And along here, we see the total number of deaths from cardiovascular disease, but this has been scaled in proportion to the number of people in each group. And what we can plot is an image of the increasing number of heart attacks and strokes that led to the patient's death in the group that did not eat many chilies, and compare that with the increasing number of fatal heart attacks and strokes in the chili-eating group. And what we can see is that this total is increasing at a slower rate in the chili-eating group compared with the non-chili-eating group. The rate at which these totals are increasing is known as the hazard. Slightly more technically, the hazard is the annual risk of dying from cardiovascular disease, although you could choose a different time period. So the hazard ratio is the hazard in the chili-eating group divided by the hazard in the non-chili-eating group, which in this study is estimated to be 0.66. Because that number is less than 1, that means that fatal heart attacks and strokes were happening at a slower rate in the chili-eating group compared with the non-chili-eating group. Hazard ratios arise naturally from a statistical technique called survival analysis, which is used in any study where you've followed people up for a long period of time to see whether they develop diseases or die or some other event. And this can be used in randomized trials of experimental drugs or in studies like this when you're trying to relate lifestyle with future events. The technical way in which hazard ratios are derived comes from what's known as Cox proportional hazards regression analysis, which is a very useful technique because it allows you to estimate hazard ratios while adjusting for other factors which might influence the risk. For example, in this chili study, they adjusted for age, sex, energy intake, educational level, occupational class, smoking, leisure time physical activity, cardiovascular disease, even consumption of garlic, parsley, and black pepper. But to know what hazard ratios mean, you don't really need to understand survival analysis and Cox regression. You just need to know that they're basically the ratio of the annual risk of an event happening in one group compared with the annual risk in another group. So, how do we communicate hazard ratios? Well, you could say that this 0.66 represents a 34% reduction in the annual risk of getting a heart attack or stroke. And 34% because that's just 1 minus 0.66. Yeah, but it's not very good. I mean, 34% reduction from what? If you want to tell a good, clear story, here's a better way. If we want to communicate what this hazard ratio of 0.66 really means to a wide audience, we have to share three things. First, how many fatal heart attacks and strokes actually occurred in each group? Second, over what time period? And third, how much chili were they actually consuming? Only by knowing these things can we get an idea of whether this research is actually important or not. What we're doing is essentially converting a hazard ratio to a difference in absolute risks. And we've got a tool, Real Risk, that'll help you do this. There's a link in the description. Now, if you run this research through Real Risk, it'll tell you that out of 100 Italian adults in their mid-50s who never eat chili, we would expect around 3 to die of cardiovascular disease over 10 years. Whereas, out of 100 Italian adults in their mid-50s who eat chili more than 4 times a week, we would expect only 2 to die of CVD over 10 years. Those are the essential things you need to know. Another way of looking at it is that 100 people eating chilies more than 4 times a week experienced 1 fewer fatal heart attack or stroke over 10 years. And of course, we don't know that it's the chili eating that led to that reduction in risk. It's just an association. Now, perhaps telling the story in this way won't lead to such dramatic headlines, but the truth rarely does.
So a hazard ratio reflects results over time. It takes into account the difference in results over the entire period of the trial, not just a specific point. Thus, it is often a better predictor of a treatment's actual effect on the entire patient population. Hazard ratios are often used for a survival analysis or survival rates. For example, they can be used in prognoses with cancer diagnosis. We saw the interpretation of the fatal heart attacks and strokes in the chili eating group and the non-chili eating group. Continued interpretation, a ratio of greater than 1 shows an increased risk of outcome with the study intervention or exposure. So in the chili case, that would mean that numerator on top, that hazard ratio was higher in the chili group instead of lower, though in reality it was lower, with a final result of 0.66, which shows that there was a reduced risk of outcome with the study intervention or exposure. If the numbers were identical, then there would be no difference in risk between intervention and control. With the chili pepper, to get more meaningful results, we needed the information of how many fatal heart attacks and strokes occurred in each group, over what time period, how much chili were they consuming in each group. With that information, we saw that our headlines may have been blown a bit out of proportion, and that over a 10-year time span, the chili pepper eating adults saw 1 fewer death from cardiovascular disease than those who did not eat chili. So I hope you're getting a grasp of the statistics you'll be finding in your results section in your studies. Today, we looked at difference statistics and ratio statistics. In difference statistics, remember, there's absolute risk reduction, number needed to treat, and number needed to harm. In ratio statistics, we talked about relative statistics, odds ratios, and hazard ratios. In the next module, we'll pull some of that together looking at confidence intervals. Please, if you have any questions or concerns, get a hold of me through my email. Happy studying.